Hello there and welcome to Theories Before Sleep. I'm so glad you're here. Maybe it's been a long day, perhaps filled with obligations and noise, or maybe your mind is still racing with thoughts that won't settle. Tonight you've come seeking something peaceful, something vast enough to make your worries feel small, gentle enough to carry you into sleep. We're going to explore 100 theories about galaxies, not in a rush, but slowly, gently, like starlight crossing the cosmos. From spiral arms to supermassive black holes, from colliding giants to the loneliest voids, each theory is a quiet doorway into wonder. Some will feel familiar, others strange and distant. All are presented to help you drift peacefully towards sleep, your mind wandering through cosmic mysteries that ask nothing of you but your presence. If these explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The first theory is waiting, patient and quiet. Galaxies form from dark matter, scaffolding. The universe might build its galaxies on invisible foundations. This theory suggests that dark matter, which we cannot see or touch, creates a gravitational skeleton throughout space. Like a spider's web catching dew, this dark scaffolding catches ordinary matter, pulling it into clumps and spirals. Over billions of years, hydrogen and helium gather in these invisible wells, eventually forming the galaxies we observe today. The dark matter remains, surrounding each galaxy like a halo we can only detect through its gravitational influence. Without this hidden architecture, galaxies might never have formed at all. The visible universe would be smooth and empty, stars scattered randomly through the void. Instead, dark matter carved channels and valleys through space, guiding matter into beautiful structures. We live inside one of these structures, our galaxy held together by something we cannot perceive, only infer from the way visible matter moves and clusters in patterns that betray an unseen hand. Spiral arms are density waves, not permanent structures. The spiral arms of galaxies might be illusions of a kind, patterns rather than things. This theory proposes that spiral arms are density waves moving through the galactic disk, like traffic jams on a cosmic highway. Stars and gas clouds don't stay in the arms permanently, but pass through them, slowing down as they enter and speeding up as they leave. The arms persist because new material constantly enters as old material departs, maintaining the pattern even as individual stars complete their orbits. This explains why spiral arms remain distinct over millions of years despite the fact that inner parts of galaxies rotate faster than outer parts, which should wind the arms tighter and tighter until they disappear. Instead, the density wave rotates at its own pace, independent of the stars, a pattern written in gravity and motion. The arms glow brightly because compression in the density wave triggers star formation, lighting up the pattern like a neon sign, making visible something that is more process than structure. Galaxies grow by consuming smaller galaxies. Our galaxy might be built from the remains of hundreds of smaller galaxies, consumed over billions of years. This theory of hierarchical formation suggests that galaxies grow through mergers and acquisitions, larger ones gravitationally capturing and absorbing smaller neighbours. Evidence appears in stellar streams, long ribbons of stars stretched around the Milky Way, the remnants of dwarf galaxies torn apart by tidal forces. Each stream tells a story of consumption, of a smaller galaxy that wandered too close and was pulled apart, its stars scattered into new orbits around our galactic centre. This process continues today, with several dwarf galaxies currently being absorbed. The theory suggests that galaxy formation is violent and ongoing, not a single event, but a continuous accumulation. Our galaxy wears the ghosts of its meals, their stars now mixed with ours, indistinguishable except through careful analysis of their orbits and compositions, which reveal their foreign origins, their history written in motion and chemistry. Supermassive black holes regulate galaxy growth. At the heart of most galaxies sits a supermassive black hole, and these giants might control how large their host galaxies can become. This theory proposes a feedback mechanism where the black hole's activity limits star formation throughout the galaxy. As matter spirals into the black hole, it heats up and emits tremendous energy, creating winds and jets that blow gas out of the galaxy or heat it too much for stars to form. This prevents the galaxy from converting all its gas into stars too quickly, regulating growth and determining the final mass of the galaxy. Observations show a tight correlation between black hole mass and the properties of the surrounding galaxy, suggesting a deep connection. The black hole and galaxy seem to grow together, each influencing the other in a cosmic dance of creation and destruction. Without this regulation, galaxies might burn through their gas reserves too quickly, leaving the universe filled with dead galaxies, their star formation exhausted billions of years ago. Galaxies exist in a cosmic web of filaments. Galaxies aren't scattered randomly through space, but arranged in a vast web-like structure spanning the observable universe. This theory describes how matter in the early universe clumped along filaments, creating a cosmic web with galaxies concentrated in dense nodes and filaments, while vast voids remain nearly empty. The structure emerged from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Simulations of cosmic evolution reproduce this web-like pattern remarkably well, suggesting the theory captures something fundamental about how structure forms in an expanding universe. The cosmic web is the largest known structure in existence, its filaments stretching hundreds of millions of light-years, connecting galaxy clusters like cities along highways. Our galaxy sits within one of these filaments, part of a structure so vast that light takes hundreds of millions of years to cross it. The web reveals the universe's hidden order, a pattern invisible to us locally, but evident when we step back and observe the distribution of galaxies across cosmic scales. Elliptical galaxies form from galaxy mergers. The smooth, football-shaped elliptical galaxies might be the products of violent collisions between spiral galaxies. This theory suggests that when two spiral galaxies merge, their orderly rotation is disrupted, stars scattered into random orbits that create an elliptical shape. The merger destroys the spiral structure, mixing the stellar populations and triggering intense bursts of star formation as gas clouds collide and compress. Eventually the system settles into a new equilibrium, a rotating ellipsoid of stars with little remaining gas and minimal ongoing star formation. Observations of colliding galaxies support this theory, showing systems in various stages of merger, their spiral arms distorted and stretched, their cores beginning to blend. In the distant future, our Milky Way will likely merge with the Andromeda Galaxy, and the resulting system will probably be an elliptical galaxy, our spiral structure erased, our stars redistributed into new orbits. The process takes hundreds of millions of years, a slow-motion collision on cosmic scales, but the outcome seems inevitable, written in the galaxy's trajectories and mutual gravitational pull. Dark energy determines the ultimate fate of galaxies. The mysterious dark energy that accelerates the universe's expansion might determine whether galaxies will remain visible to each other forever or drift apart into isolation. This theory suggests that as dark energy continues pushing space to expand faster and faster, distant galaxies will eventually recede beyond our cosmic horizon, their light unable to reach us no matter how long we wait. Galaxies not bound together by gravity will lose contact, each galaxy or galaxy cluster becoming an island universe, alone in an expanding void. Within billions of years, observers in distant galaxies will see only their local group, the rest of the universe having disappeared beyond reach. This cosmic isolation is already beginning, with the most distant galaxies we can currently observe receding at nearly the speed of light. The theory paints a lonely future for the universe, vast structures separated by expanding space that grows faster than light can cross it, each galaxy cluster eventually alone, surrounded by darkness, unaware that other galaxies exist elsewhere in the void. Galaxies might contain parallel stellar disks. Some theories suggest that galaxies might harbour multiple overlapping disks of stars, each rotating independently at different angles. This idea emerged from observations of galaxies with unusual kinematics, where stars seem to move in two distinct populations with different angular momenta. The theory proposes that these disks formed from separate accretion events, gas falling into the galaxy from different directions at different times, each settling into its own orbital plane. The disks would pass through each other like ghosts, their stars almost never colliding due to the vast distances between them, but their combined gravity shaping the galaxy's overall structure. Such systems would be difficult to detect from our external vantage point, requiring careful analysis of stellar velocities to reveal the hidden structure. If common, parallel disks would suggest that galaxy formation is even more complex than currently thought. With multiple episodes of gas accretion creating layered structures, each disk a separate chapter in the galaxy's history, all coexisting in the same space, invisible to each other except through gravity's patient pull. Galaxies form stars in episodic bursts, not continuously. Star formation in galaxies might not be a steady process, but occurs in bursts triggered by specific events. This theory suggests that galaxies alternate between active and quiescent phases, forming stars rapidly during bursts and then remaining relatively dormant for long periods. The bursts might be triggered by galaxy interactions, gas accretion events, or internal instabilities that compress gas and trigger widespread star formation. Between bursts, the galaxy recovers, accumulating new gas and settling into a stable configuration until the next trigger arrives. Observations of galaxies at different distances, and thus different times in cosmic history, show a wide range of star formation rates, supporting the idea that star formation varies dramatically over time. Some galaxies appear caught mid-burst, their disks lit up with young, bright stars, while others seem quiet, their star formation reduced to a trickle. This episodic nature might explain why galaxies of similar mass can look so different, each caught at a different phase in its cycle, some actively forming stars, others resting, waiting for the next burst to begin. Galactic bars drive. Gas toward the center. Many spiral galaxies, including our own, contain a bar-shaped structure of stars stretching across their centers, and this bar might play a crucial role in the galaxy's evolution. The theory proposes that the bar's gravitational field funnels gas from the outer disk toward the galactic center, feeding star formation in the nucleus and potentially feeding the central black hole. The bar rotates as a solid structure, its pattern speed different from the orbital speeds of individual stars, creating resonances that trap gas and drive it inward along the bar's length. This process might explain the intense star formation observed in many galactic centers and the growth of central bulges over time. Bars are common in spiral galaxies, suggesting they represent a natural phase in galactic evolution. They might form from instabilities in the disk, emerging when the disk reaches a certain mass or density. Once formed, the bar redistributes matter within the galaxy, reshaping the disk and altering the galaxy's future evolution, a self-organizing structure that channels matter and energy, transforming the galaxy from within. If your mind is starting to wander, that's perfectly fine. These theories aren't meant to be memorized, only experienced, like watching clouds drift across the sky. Tidal forces strip, gas from satellite, galaxies. Small galaxies orbiting larger ones might lose their gas through tidal stripping, a process where gravitational forces pull material away from the smaller galaxy. This theory explains why many satellite galaxies appear gas-poor and unable to form new stars. As the satellite orbits through the halo of the larger galaxy, tidal forces stretch it, pulling gas from its outer regions. The stripped gas forms streams and clouds that eventually fall into the larger galaxy, fueling its star formation. The satellite galaxy, deprived of raw material, gradually stops forming stars and fades, its stellar population aging without replacement. This process is observed in the Milky Way's satellite galaxies, many of which show signs of tidal disruption and gas loss. The theory suggests that small galaxies in dense environments face a harsh future, their gas reserves stolen by their larger neighbours, their star formation quenched, leaving them as dim collections of old stars, relics of what they once were, orbiting as ghosts around the galaxy that consumed their future. Galaxies might form around ancient quasar seeds. Some theories propose that the supermassive black holes at galactic centres formed first, and galaxies grew around them like pearls around grains of sand. In this view, massive black holes formed in the early universe from direct collapse of gas clouds or from the remnants of the first generation of stars. These black holes then accreted matter, shining as quasars and attracting more gas through their gravity. The accumulated gas eventually formed stars, building a galaxy around the central black hole. This reverses the traditional view where galaxies form first and black holes grow within them. The theory might explain why black hole mass correlates so tightly with galaxy properties, suggesting a more fundamental connection than mere coincidence. If true, black holes aren't passengers in galaxies, but they're architects, the seeds around which cosmic structure crystallized. The brightest objects in the early universe, quasars, would mark sites of future galaxy formation, beacons showing where matter was gathering, where the next generation of galaxies would emerge from the cosmic fog. Ram pressure stripping removes gas from galaxies in clusters. Galaxies moving through galaxy clusters might lose their gas through ram pressure, like a car driving through rain. This theory describes how the hot, diffuse gas-filling galaxy clusters creates a headwind for galaxies moving through it. The pressure from this headwind strips gas from the galaxy's disk, removing the raw material for star formation and leaving the galaxy gas-poor and red. The stripped gas forms long tails behind the galaxy, visible in certain wavelengths marking the galaxy's path through the cluster. This process, called ram pressure stripping, is most effective in dense cluster cores where the intergalactic gas is hottest and densest. Observations show many cluster galaxies with stripped gas tails and reduced star formation, supporting the theory. The process transforms spiral galaxies into red, dead systems, their blue colour fading as their star formation ceases, their disks cleared of gas by the relentless pressure of their environment. The theory explains why cluster galaxies look different from isolated galaxies, their evolution shaped by their surroundings, their futures determined by where they live in the cosmic web. Galaxies might be stabilized by dark matter, cusps. The distribution of dark matter within galaxies might determine their stability and structure. This theory suggests that dark matter forms a cusp, a sharp increase in density toward the galactic center, and this cusp provides gravitational stability to the visible disk of stars and gas. Without the dark matter cusp, the disk might be unstable, prone to developing bars or spiral arms that would disrupt its structure. The cusp acts like a gyroscope, its concentrated mass at the center keeping the galaxy rotating smoothly. However, observations of some galaxies suggest flatter dark matter cores rather than cusps, creating a tension between theory and observation. This discrepancy, known as the cusp core problem, remains unresolved. Perhaps dark matter behaves differently than simulations predict, or perhaps feedback from star formation and supernovae redistributes dark matter, smoothing out the cusp over time. The answer will reveal something fundamental about dark matter's nature and its role in shaping galaxies, a mystery written in the invisible scaffolding that holds galaxies together. Galactic winds recycle matter. Between galaxies and intergalactic space star formation and supernova explosions might drive powerful winds that blow gas out of galaxies and into the surrounding space. This theory proposes that these galactic winds are crucial for regulating star formation and enriching the intergalactic medium with heavy elements, The winds, powered by the collective energy of millions of supernovae and stellar winds, can reach speeds of thousands of kilometers per second, fast enough to escape the galaxy's gravity. The expelled gas carries metals forged in stars, spreading them through intergalactic space. Eventually, this enriched gas might fall back into galaxies, recycled and ready to form new stars, creating a fountain of matter between galaxies and their surroundings. This recycling process might be essential for understanding why galaxies don't convert all their gas into stars at once. The winds provide a self-regulating mechanism, preventing runaway star formation and extending the star formation process over billions of years. The theory suggests galaxies are not closed systems, but exchange matter with their environment, breathing in and out, connected to the larger cosmic ecosystem. Galaxies follow a fundamental plane relationship. Elliptical galaxies seem to follow a tight relationship between their size, brightness, and internal velocity dispersion, called the fundamental plane. This theory suggests that this relationship reflects something deep about how galaxies form and evolve. The fundamental plane is like a cosmic equation that all elliptical galaxies obey, regardless of their individual histories. The relationship is so tight that it can be used to measure distances to galaxies, assuming that deviations from the plane indicate distance rather than intrinsic differences. Why galaxies follow this relationship remains somewhat mysterious, but it likely reflects the balance between gravity, which holds the galaxy together, and the kinetic energy of stars moving within it. The fundamental plane suggests that despite their diverse appearances and histories, elliptical galaxies are fundamentally similar objects, governed by the same physics, shaped by the same processes. It's a hint that beneath the apparent diversity of the cosmos lies a deeper simplicity, patterns that emerge from universal laws, order hidden in the chaos of galaxy formation and evolution. Satellite galaxies might be distributed in planar structures. The small galaxies orbiting larger ones might not be randomly distributed, but arranged in thin, rotating planes. A surprising pattern that challenges standard cosmological models. This theory emerged from observations of the Milky Way's satellites, many of which seem to orbit in a flattened structure rather than a spherical distribution. Similar patterns have been observed around other galaxies, suggesting this might be a common feature. The origin of these planes remains debated. Perhaps satellites form from the fragmentation of a larger structure, or maybe they're captured along specific trajectories determined by the cosmic web's geometry. The planar distribution is difficult to explain in standard dark matter models, which predict more spherical distributions. This tension might indicate something missing in our understanding of galaxy formation, or it might suggest that dark matter behaves differently than assumed. The mystery of satellite planes remains one of the puzzles in galactic astronomy, a pattern that seems too organized to be random, too specific to be coincidence, yet too strange to explain easily with current theories. Galaxies might contain intermediate mass black holes in their disks. Besides the supermassive black holes at their centers, galaxies might harbor smaller but still massive black holes scattered throughout their disks. These intermediate mass black holes, thousands to hundreds of thousands of times the Sun's mass, could form from the collapse of dense star clusters or from the merger of smaller black holes. The theory suggests these objects might be common but difficult to detect because they don't emit much light unless they're actively feeding on surrounding gas. If they exist, intermediate mass black holes would influence the dynamics of their surroundings, creating small-scale disturbances in the galactic disk. They might also serve as seeds for supermassive black holes, growing over time through accretion and mergers. Some observations hint at their existence, including unusual X-ray sources and the dynamics of certain star clusters, but definitive proof remains elusive. The theory proposes a population of invisible architects scattered through galaxies, their gravity shaping local structure, their presence betrayed only by subtle effects on surrounding matter, ghosts in the galactic machinery. dark matter might explain galaxy rotation curves. The way galaxies rotate presents a puzzle that dark matter might solve. Observations show that stars and gas in the outer regions of galaxies orbit faster than expected based on the visible matter alone. This theory proposes that galaxies are embedded in massive halos of dark matter, extending far beyond the visible disk, and this dark matter's gravity keeps outer regions rotating faster than they otherwise would. Without dark matter, the outer stars should move more slowly, like outer planets in the solar system. Instead, rotation curves remain flat, indicating constant orbital velocity regardless of distance from the center. This flat rotation curve is one of the strongest pieces of evidence for dark matter's existence. The theory suggests that visible galaxies are just the bright centers of much larger dark matter structures, like lighthouses on dark islands. The dark matter halo might contain 10 times more mass than all the visible stars and gas combined, an invisible ocean in which galaxies float, their rotation curves revealing the hidden mass that holds them together. Galaxies might merge without triggering star formation. Not all galaxy mergers might trigger the intense bursts of star formation typically associated with collisions. This theory suggests that gas-poor galaxies, like ellipticals, can merge relatively quietly, their stellar populations mixing without significant new star formation. These dry mergers, as they're called, might be common in the present-day universe where many galaxies have already converted most of their gas into stars. The merger still redistributes stars and dark matter, potentially growing the central black hole and altering the galaxy structure, but without the fireworks of a gas-rich merger. Dry mergers might be important for building the most massive elliptical galaxies in the universe, which seem too large to have formed from single gas-rich mergers. Instead, they might grow through multiple dry mergers, accumulating mass without triggering star formation. The theory suggests that galaxy evolution continues even after star formation ceases, that galaxies remain dynamic objects throughout cosmic time, their structures and masses changing through interactions even when they have exhausted their gas, still evolving, still growing, still dancing with their neighbours in the cosmic dark. Galactic magnetic fields might regulate star formation. Galaxies possess large-scale magnetic fields that might play a crucial role in regulating where and when stars form. This theory proposes that magnetic fields provide support against gravitational collapse in gas clouds, preventing them from fragmenting into stars too quickly. The fields thread through the galactic disk, their strength and structure influencing the dynamics of the interstellar medium. In regions where the field is strong, gas might resist collapse, reducing star formation. Where the field is weak or tangled, collapse proceeds more easily. The theory suggests magnetic fields act as a throttle on star formation, working alongside other processes like turbulence and feedback from existing stars. Observations show that magnetic fields in galaxies are indeed strong enough to affect gas dynamics, with field strengths comparable to the energy density of turbulent motions. Understanding how these fields are generated and maintained remains a challenge, but they likely arise from dynamo processes, where the galaxy's rotation and turbulence amplify weak seed fields into the large-scale structures observed today, invisible lines of force shaping the visible cosmos. Galaxies might experience secular evolution. Even without major mergers, galaxies might evolve significantly through internal processes over billions of years. This theory of secular evolution describes how bars, spiral arms, and internal instabilities gradually redistribute matter within a galaxy, changing its structure and appearance. Unlike the violent transformation of a merger, secular evolution is slow and steady, driven by gravitational interactions between different components of the galaxy. Bars transport gas inward, building up the central bulge. Spiral arms trigger star formation, enriching the disk with metals. These processes operate continuously, subtly reshaping the galaxy over cosmic time. The theory suggests that a galaxy's present appearance reflects not just its formation and merger history, but also billions of years of internal evolution. A spiral galaxy today might look quite different in a few billion years, even if it never merges with another galaxy, its structure transformed by its own internal dynamics. Secular evolution emphasizes that galaxies are not static objects, but living systems, constantly changing, constantly evolving, shaped by forces from within as much as by interactions from without, patient architects of their own transformation. Cosmic rays from galaxies might influence their evolution. High-energy particles called cosmic rays, produced by supernovae and other violent events in galaxies, might play an underappreciated role in galactic evolution. This theory proposes that cosmic rays provide significant pressure support in the galactic disk, helping to stabilize gas clouds against collapse and potentially driving galactic winds. The cosmic ray pressure, comparable to thermal and magnetic pressure in some regions, affects the dynamics of the interstellar medium in ways that simulations are only beginning to include. Cosmic rays can also influence the chemistry of the interstellar medium, affecting molecule formation and potentially altering where and how stars form. They might help launch galactic winds by providing additional pressure to push gas out of the galaxy. The theory is still developing, as cosmic rays are difficult to observe directly and challenging to include in simulations, but their energy density suggests they cannot be ignored. They represent another invisible component of galaxies, like dark matter and magnetic fields, shaping evolution in subtle ways, their influence written in the structure and dynamics of the visible matter we observe. Galaxies might form through cold flows in the early universe. In the early universe, galaxies might have grown by accreting cold gas that flowed directly from the intergalactic medium along filaments of the cosmic web. This theory of cold mode accretion suggests that in the past, gas didn't need to be shock heated to millions of degrees before falling into galaxies. Instead, cold streams of gas, only thousands of degrees, flowed along dark matter filaments directly into galaxies, providing a steady supply of fuel for star formation. This process would have been most important when the universe was younger and denser, and it might explain the high star formation rates observed in distant galaxies. As the universe expanded and the intergalactic medium heated up, cold mode accretion became less efficient, and galaxies had to rely more on internal gas reserves or on recycled gas from galactic fountains. The theory paints a picture of young galaxies as hungry organisms, feeding on streams of cold gas flowing through the cosmic web, growing rapidly in their youth before the streams dried up and their growth slowed, leaving them to age on their accumulated reserves. Galactic bulges might form from disk instabilities. The central bulges of spiral galaxies might not all form from mergers, but could grow from instabilities within the disk itself. This theory proposes that when a galactic disk reaches a certain mass or density, it becomes unstable and develops a bar or other non-axis symmetric structure. These structures drive gas toward the center, triggering star formation and building up a central concentration of stars. Over time, the bar might dissolve or weaken, leaving behind a bulge that looks similar to those formed in mergers but has a different origin. This process, called pseudo-bulge formation, might be common in spiral galaxies. Pseudobulges tend to be flatter and more disk-like than classical bulges, and they often show evidence of ongoing star formation, unlike the old stellar populations in merger-formed bulges. The theory suggests that not all bulges are created equal, that there are multiple pathways to building a galactic center, each leaving different signatures in the structure and stellar populations. Understanding which bulges formed from which process helps reconstruct the histories of individual galaxies, reading their past in their present structure. Galaxies might undergo morphological quenching. A galaxy's shape might determine whether it continues forming stars or becomes quiescent. This theory of morphological quenching suggests that when a galaxy develops a large bulge, The bulge's gravity stabilizes the disk against the formation of new stars. The bulge creates a deep gravitational potential well that prevents gas from fragmenting easily, reducing star formation throughout the galaxy. This could explain why elliptical galaxies and spiral galaxies with large bulges tend to be redder and form fewer stars than bulgeless spirals. The theory provides a mechanism for shutting down star formation that doesn't require external influences like ram pressure stripping or tidal interactions. Instead, the galaxy's own structure determines its fate, a form of self-quenching where growth eventually chokes off further growth. Morphological quenching might work in concert with other mechanisms, creating a complex web of processes that determine when and how galaxies stop forming stars. The theory suggests that a galaxy's destiny might be written in its shape, that structure and evolution are intimately connected, each influencing the other in an endless feedback loop. If your eyes are growing heavy, don't fight it. Sleep is welcome here. The theories will continue whether you hear them or not, a quiet voice in the darkness. Galaxies might contain dark disks. Some theories propose that galaxies might contain disks made entirely of dark matter, rotating alongside the visible stellar disk. These dark disks would form if dark matter particles can interact with each other through forces other than gravity, allowing them to lose energy and settle into a disk like ordinary matter does. Most dark matter models assume dark matter is collisionless, unable to dissipate energy, and thus remaining in a spherical halo. But if dark matter has even weak self-interactions, a fraction might settle into a disk, potentially affecting the galaxy's dynamics and structure. A dark disk could influence the orbits of stars, especially those moving perpendicular to the galactic plane. It might also affect the distribution of dark matter in the galaxy's center. Detecting a dark disk would be challenging, requiring careful measurement of stellar motions and comparing them to predictions. The theory remains speculative, but it highlights how much we still don't know about dark matter's properties. A dark disk would be a ghost structure, invisible but influential, a hidden twin to the visible galaxy, felt but never seen. Galaxies might experience quasar-mode feedback. The supermassive black holes at galactic centers might go through phases of intense activity that dramatically affect their host galaxies. This theory of quasar-mode feedback describes how a black hole, when fed large amounts of gas, shines as a quasar and produces powerful jets and winds that heat or expel gas from the galaxy. This feedback can shut down star formation across the entire galaxy, transforming it from blue and star-forming to red and quiescent. The quasar phase might be triggered by galaxy mergers, which funnel gas toward the central black hole, or by other instabilities that deliver fuel to the nucleus. Once the quasar turns on, its energy output can exceed the entire galaxy's stellar luminosity, and its influence extends throughout the system. The theory explains the observed correlation between black hole mass and galaxy properties, suggesting that black holes regulate their own growth and their galaxy's evolution through feedback. Quasar-mode feedback might be responsible for creating the population of massive red dead galaxies observed in the universe, galaxies that stopped forming stars billions of years ago, their futures determined by a brief but intense phase of black hole activity. Galaxies might form in waves. Across cosmic time, galaxy formation might not have been a single event, but occurred in waves, with different populations of galaxies forming at different times. This theory describes how the first galaxies formed from pristine gas in the early universe, creating stars from hydrogen and helium alone. These first galaxies were small and metal-poor. Later generations formed from gas enriched by the first stars' deaths, allowing them to form different types of stars and develop different structures. Each generation of galaxies inherited the chemical legacy of previous generations, building on what came before. The theory suggests that looking at galaxies of different ages is like looking at different chapters in a story, each chapter building on the last, each generation shaped by the environment created by its predecessors. The most distant galaxies we observe, seen as they were billions of years ago, represent early chapters, while nearby galaxies represent the present chapter. Understanding this cosmic narrative requires piecing together observations across vast stretches of space and time, reading the universe's history in the light from galaxies at different distances. Galactic halos might extend much farther than visible disks. The dark matter halo surrounding galaxies might extend to distances many times larger than the visible galaxy, creating vast spheres of invisible matter. This theory suggests that what we see as a galaxy is just the bright center of a much larger structure. The halo might extend hundreds of thousands of light-years from the galactic center, far beyond the stellar disk. Within this halo, dark matter dominates, outweighing visible matter by factors of 10 or more. The halo's gravity influences satellite galaxies, determining their orbits and their eventual fate. It also affects how galaxies interact with each other, as their halos can overlap and interact even when their visible disks are still far apart. The theory proposes that galaxies are much larger than they appear, that the visible light traces only a small fraction of the total structure. Understanding halo properties requires indirect methods, like studying satellite galaxy orbits or measuring gravitational lensing effects. These halos are the true extent of galaxies, invisible boundaries that define where one galaxy ends and intergalactic space begins, or perhaps where one galaxy blends into the next, boundaries that might not be sharp but gradual. Galaxies might undergo inside-out growth. Galaxies might build themselves from the center outward, with the inner regions forming stars first and the outer regions forming stars later. This theory of inside-out growth suggests that gas settles into the galactic center first, where it's densest and star formation proceeds most rapidly. Over time, as more gas accretes and angular momentum redistributes matter, the disk grows outward, extending the star-forming region to larger radii. This process would create a gradient in stellar ages, with the oldest stars concentrated in the center, and younger stars populating the outer disk. Observations of nearby galaxies show evidence for such age gradients, supporting the inside-out growth scenario. The theory also predicts that the chemical composition of stars should vary with radius, as the outer disk forms from gas that's been enriched by previous generations of stars in the inner galaxy. Inside-out growth provides a framework for understanding how galaxies reach their present sizes, and why their properties vary with radius. It suggests that galaxies are not uniform objects, but have structure in time as well as space, each region recording a different era in the galaxy's history. Galaxies might lose their dark matter. Through tidal interactions, small galaxies interacting with larger ones might lose not just their gas and stars, but also their dark matter through tidal stripping. This theory proposes that the outer parts of a satellite galaxy's dark matter halo can be stripped away by the tidal field of the host galaxy, similar to how gas and stars are stripped. Over multiple orbits, the satellite might lose most of its dark matter halo, leaving behind a compact remnant with a much lower dark matter content than expected. This process might create dark matter streams flowing through the host galaxy's halo, analogous to the stellar streams observed from disrupted satellites. The stripped dark matter would be difficult to detect directly, but might be inferred from its gravitational effects or from simulations that predict its distribution. The theory suggests that dark matter, despite being collisionless, can still be redistributed through gravitational interactions. That dark matter halos are not permanent structures but can be torn apart and scattered, their matter recycled into the larger halo surrounding them, contributing to the host galaxy's dark matter reservoir. Galaxies might form stars more efficiently at certain masses. There might be a characteristic galaxy mass where star formation is most efficient, with both more massive and less massive galaxies converting their gas into stars less efficiently. This theory attempts to explain the observed galaxy mass function, which shows a characteristic turnover at a certain mass scale. Above this mass, galaxies are increasingly rare, suggesting that something prevents them from forming stars efficiently. Below this mass, galaxies are also less efficient at forming stars, perhaps because their shallow gravitational potential wells make it easier for feedback processes to expel gas. The theory proposes that there's a sweet spot where gravity is strong enough to retain gas against feedback, but not so strong that the galaxy quickly exhausts its gas supply. This characteristic mass might correspond to the scale where various feedback processes balance most effectively, creating a natural limit to efficient galaxy growth. Understanding why this scale exists requires understanding the complex interplay between gravity, gas cooling, star formation, and feedback, all of which vary with galaxy mass, creating a landscape of star formation efficiency that peaks at intermediate masses. Galaxies might host multiple populations of stars with different origins. A single galaxy might contain several distinct populations of stars formed at different times or from different sources. This theory suggests that galaxies are composites, built from stars formed in situ from the galaxy's own gas, as well as stars captured from smaller galaxies that merged with the host. Each population would have different chemical compositions, ages and kinematic properties, reflecting their different origins. The theory can explain the complex structure observed in many galaxies, where different components seem to have different characteristics. For example, the thick disk of the Milky Way might be composed partly of stars formed during an early phase of intense star formation, and partly of stars captured from accreted satellites. Disentangling these populations requires detailed observations of individual stars, measuring their compositions, ages, and motions. The theory paints galaxies as archaeological sites, containing layers of history written in their stellar populations, each layer telling a different part of the story, each population a chapter in the galaxy's biography, all coexisting in the same space, their origins revealed only through careful study. Galaxies might be shaped by turbulence in the interstellar medium. The chaotic, turbulent motions of gas within galaxies might play a crucial role in determining their structure and evolution. This theory proposes that turbulence, driven by supernova explosions, stellar winds, and gravitational instabilities, creates a complex, ever-changing structure in the interstellar medium. This turbulence affects how gas collapses to form stars, potentially regulating the rate of star formation and determining where stars form. Turbulent energy can support gas clouds against gravitational collapse, preventing them from forming stars too quickly. At the same time, turbulent compression can trigger star formation by creating dense regions where gravity can overcome pressure support. The theory suggests that turbulence is not just noise in the system, but a fundamental driver of galactic evolution, comparable in importance to gravity itself. Understanding turbulence in the interstellar medium requires sophisticated simulations, as the turbulent cascade spans a vast range of scales, from galaxy-wide motions down to the smallest clouds. The turbulence makes the interstellar medium a dynamic, living environment, constantly churning, constantly changing, never settling into equilibrium, a cosmic storm that never ends. Galaxies might follow different evolutionary tracks based on environment. Where a galaxy lives might determine how it evolves, with galaxies in dense clusters following different evolutionary paths than isolated galaxies. This theory of environmental dependence suggests that galaxies and clusters experience ram pressure stripping, tidal interactions, and galaxy harassment, all of which can remove gas, trigger or suppress star formation, and alter morphology. Meanwhile, isolated galaxies evolve more peacefully, their evolution driven primarily by internal processes and occasional minor mergers. The theory predicts that cluster galaxies should be redder, more gas-poor, and more likely to be elliptical than field galaxies, which is indeed observed. The environment acts as a sculptor, shaping galaxy evolution through external forces that don't affect isolated galaxies. Understanding environmental effects is crucial for building a complete picture of galaxy evolution, as a galaxy's destiny depends not just on its mass and initial conditions, but also on where it happens to live in the cosmic web. Some neighborhoods are harsh, stripping galaxies of their gas and transforming them into red, dead systems. Other neighborhoods are gentle, allowing galaxies to evolve at their own pace, forming stars for billions of years. Their evolution determined from within rather than imposed from without. Galaxies might contain fossil records of their formation. The oldest stars in a galaxy might preserve information about the conditions when the galaxy formed, serving as fossil records of the early universe. This theory suggests that by studying the chemical compositions and spatial distributions of these ancient stars, we can learn about the first episodes of star formation in the galaxy, the properties of the gas from which they formed, and the environment in which the galaxy assembled. The oldest stars are metal poor, formed from gas that had been enriched by only a few generations of stars, and their compositions reflect the nucleosynthesis yields of the first supernova. Their orbits might reveal the structure of the early galaxy, before later evolution redistributed stars and altered the galaxy's shape. Finding and studying these fossil stars requires surveying large numbers of stars and identifying the rare ancient ones. But the effort provides a unique window into the galaxy's youth. These stars are time capsules carrying information across billions of years, their light a message from the distant past, their existence a connection to the earliest moments of the galaxy's history, witnesses to events long vanished but not forgotten. If some theories feel confusing, that's okay. They're meant to be felt more than understood, like music you don't need to analyze to enjoy. Galaxies might experience cosmic downsizing. The most massive galaxies might have formed their stars earliest in cosmic history, while less massive galaxies continue forming stars to the present day. This theory of cosmic downsizing seems counterintuitive, as one might expect massive galaxies to take longer to assemble. However, observations suggest that massive galaxies were already red and dead when the universe was young, while lower mass galaxies were still actively forming stars. The theory proposes that massive galaxies formed in the densest regions of the early universe, where gas could collapse and form stars rapidly. These galaxies quickly exhausted their gas supplies, or had their star formation shut down by feedback processes. Lower mass galaxies formed in less dense regions, and have evolved more slowly, some continuing to form stars even today. Cosmic downsizing implies that the peak of star formation activity has shifted from massive galaxies in the early universe to less massive galaxies in the present day. This pattern challenges simple models of hierarchical galaxy formation and suggests that galaxy evolution is more complex than initially thought, with mass and environment both playing crucial roles in determining when galaxies form their stars. Galaxies might be regulated by cosmic feedback loops. The evolution of galaxies might be governed by feedback loops that connect star formation, black hole growth, and gas content in complex ways. This theory proposes that galaxies exist in a delicate balance, where star formation heats and expels gas, reducing future star formation, but also enriches the gas with metals, potentially making future star formation more efficient. Similarly, black hole growth produces feedback that can quench star formation, but the black hole's growth depends on gas being funneled to the center, which might require star formation to drive the necessary instabilities. These feedback loops create a self-regulating system where galaxies adjust their star formation rates and black hole growth to maintain a kind of equilibrium. The theory suggests that understanding galaxy evolution requires understanding these interconnected processes, not as separate phenomena but as parts of an integrated system. Galaxies are not passive objects shaped only by external forces, but active participants in their own evolution, constantly adjusting and responding to internal conditions, their futures determined by the complex interplay of multiple processes, each affecting the others. creating patterns that emerge from the whole system rather than from any single component. Galaxies might undergo rejuvenation through gas accretion. Galaxies that have stopped forming stars might be rejuvenated if they accrete new gas from their surroundings. This theory suggests that galaxies in the present-day universe might capture cold gas from the intergalactic medium or from interactions with gas-rich companions, reigniting star formation after a period of quiescence. The accreted gas would provide fresh fuel, allowing the galaxy to form a new generation of stars and potentially transforming its appearance from red and dead to blue and active. Observations of some galaxies show evidence for recent gas accretion, including young stellar populations in otherwise old galaxies and gas disks, with compositions different from the galaxy's existing stars. The theory implies that galaxy evolution is not a one-way street, from star forming to quiescent, but can include reversals and renewals. A galaxy's history might include multiple episodes of star formation, separated by quiescent periods, creating a complex stellar population with multiple age components. Rejuvenation adds another layer of complexity to galaxy evolution, suggesting that even old galaxies retain the potential for new beginnings, that the future is not entirely determined by the past, that change remains possible even after billions of years. Galaxies might form through monolithic collapse. An alternative to hierarchical formation suggests that some galaxies, particularly massive ellipticals, might have formed through rapid collapse of a large gas cloud in the early universe. This theory of monolithic collapse proposes that these galaxies formed most of their stars in a single intense burst, early in cosmic history, then evolved passively afterward, their stellar population simply aging without significant new star formation or major mergers. The theory was more popular before observations revealed the prevalence of galaxy mergers, but it might still apply to certain galaxies or certain components of galaxies. For example, the central bulges of some galaxies might have formed through monolithic collapse, even if the outer disk assembled gradually. The theory predicts that galaxies formed this way should have old, uniform stellar populations with little variation in age or composition. While most galaxies show evidence for more complex formation histories involving multiple episodes and mergers, monolithic collapse might represent one extreme of the galaxy formation spectrum, a limiting case that some galaxies approach if not fully achieve, a reminder that nature might use multiple pathways to build galaxies, not just one universal process. Galaxies might contain streams of stars from cannibalized satellites. The halos of large galaxies might be crisscrossed with streams of stars, the remnants of smaller galaxies that were torn apart and consumed. This theory proposes that these stellar streams are common features of galactic halos, revealing the violent history of galaxy growth through accretion. Each stream represents a smaller galaxy that wandered too close and was destroyed by tidal forces. Its stars stretched into a long ribbon that wraps around the host galaxy. These streams are difficult to detect because they're faint and diffuse, but surveys of the Milky Way's halo have revealed several, and similar structures are expected around other large galaxies. The streams preserve information about the orbit and properties of the destroyed satellite, allowing astronomers to reconstruct the merger history of the host galaxy. The theory suggests that galactic halos are graveyards, filled with the ghosts of consumed galaxies, their stars now orbiting in patterns that trace their final moments. These streams are evidence of the hierarchical nature of galaxy formation, proof that large galaxies grew by consuming smaller ones, their current mass accumulated over billions of years through countless acts of cosmic cannibalism. Galaxies might have different star formation, histories based on their spin. The angular momentum of a galaxy might determine how efficiently it forms stars and what morphology it develops. This theory proposes that galaxies with high angular momentum form extended disks where gas settles into stable orbits and forms stars gradually over billions of years. Galaxies with low angular momentum form compact systems where gas falls to the center quickly and forms stars in an intense burst, potentially creating an elliptical galaxy. The theory connects a galaxy's initial conditions, particularly its spin, to its eventual structure and star formation history. Angular momentum might be set during the galaxy's formation, determined by the tidal torques from surrounding structure in the cosmic web. Once set, the angular momentum influences how gas behaves within the galaxy, whether it can settle into a disk or falls directly to the center. The theory provides a framework for understanding why galaxies with similar masses can have very different morphologies and star formation histories. It suggests that a galaxy's destiny is partly written in its rotation, that the spin imparted during formation echoes through billions of years of evolution, shaping the galaxy's structure and determining how and when it forms its stars. Galaxies might be affected by cosmic rays from neighboring galaxies. Cosmic rays produced in one galaxy might escape and influence neighboring galaxies, creating a form of intergalactic feedback. This theory proposes that cosmic rays, which can travel vast distances through intergalactic space, might heat gas in nearby galaxies or in the intergalactic medium, affecting star formation and gas dynamics beyond the galaxy where they originated. The cosmic rays would carry energy away from the source galaxy, distributing the energy of supernovae and other violent events across larger volumes of space. This process might be particularly important in galaxy clusters, where galaxies are close together and cosmic rays from multiple galaxies might overlap. The theory is speculative and difficult to test, as cosmic rays are challenging to observe directly, but it highlights the possibility that galaxies might not evolve in isolation even when they're not directly interacting. Instead, they might be connected through invisible channels of high-energy particles, their evolution influenced by events in neighboring galaxies. A cosmic community where energy and influence flow between members, connecting them in ways we're only beginning to understand, adding another layer of complexity to the already intricate story of galaxy evolution. Galaxies might form in filaments. Before falling into clusters, galaxies might form along the filaments of the cosmic web, and only later fall into galaxy clusters, with their properties already determined by their time in the filament. This theory suggests that the filament environment plays a crucial role in galaxy evolution, potentially pre-processing galaxies before they enter clusters. In filaments, galaxies might experience moderate density environments, frequent interactions with other galaxies, and gas accretion from the filament itself. These conditions could affect star formation, morphology, and gas content, preparing galaxies for their eventual arrival in a cluster. By the time they fall into the cluster, some galaxies might already be gas-poor and quiescent, their transformation having occurred in the filament rather than in the cluster itself. This theory complicates the picture of environmental effects on galaxies, suggesting that a galaxy's current environment might not be the primary influence on its properties. Instead, its history of environments, including time spent in filaments, contributes to its present state. Understanding galaxy evolution requires tracing galaxies' paths through the cosmic web, following their journeys from their formation sites to their present locations, accounting for all the environments they've experienced along the way. Galaxies might contain primordial gas from the Big Bang. Some gas in galaxies might be pristine material from the Big Bang, never processed through stars or enriched with heavy elements. This theory proposes that galaxies can accrete primordial gas from the intergalactic medium throughout their lives, mixing it with gas that's been recycled through stars. The primordial gas would be composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements produced in the Big Bang. Detecting this primordial gas is challenging because it mixes with enriched gas, but its presence might be inferred from observations of very metal-poor stars or gas clouds. The theory suggests that star formation in galaxies isn't entirely a process of recycling existing material, but includes fresh input from the universe at large. This primordial gas represents a connection to the earliest moments of cosmic history, material that has survived unchanged for billions of years, now finally being incorporated into stars. Its presence reminds us that galaxies are not closed systems but open ones, exchanging matter with the larger universe, their composition reflecting both their internal history and their ongoing interaction with the cosmos around them. Galaxies might experience starburst phases, triggered by interactions. Brief but intense episodes of star formation, called starbursts, might be triggered when galaxies interact or merge. This theory proposes that gravitational interactions compress gas, driving it toward the galaxy center and triggering rapid star formation that can consume a significant fraction of the galaxy's gas in a relatively short time. The starburst phase might last only a few 100 million years, but can form as many stars as the galaxy would normally form in several billion years of quiescent star formation. Starbursts are observed in many interacting galaxy systems, their intense star formation making them bright in infrared and ultraviolet light. The theory suggests that starbursts represent a distinct mode of star formation, different from the steady, disk-wide star formation seen in normal spiral galaxies. After the starburst, the galaxy might be left gas-poor and quiescent, its star formation shut down until it can accrete new gas. Starburst galaxies might represent a transition phase in galaxy evolution, systems caught in the act of transforming from star-forming to quiescent, their intense activity a brief but important episode in their history, a moment of transformation between two longer periods of calmer evolution. Galaxies might have their star formation quenched by strangulation. A galaxy's star formation might be shut down, not by removing its existing gas, but by cutting off its supply of new gas from the intergalactic medium. This theory of strangulation, or starvation, proposes that galaxies in dense environments might be unable to accrete fresh gas, causing them to gradually exhaust their existing gas supply through star formation without replenishment. The galaxy would slowly fade from blue to red as its star formation rate declines, eventually becoming quiescent when all available gas is consumed or expelled by feedback. Strangulation might be more common than rapid stripping processes in some environments, particularly in the outskirts of galaxy clusters where ram pressure is weaker. The theory predicts a gradual transition from star-forming to quiescent, with galaxies spending significant time in a transitional state. Observations of galaxies in different environments show evidence for such gradual quenching, supporting the strangulation scenario. The theory emphasizes that quenching doesn't always require violent removal of gas, but can occur through the more subtle process of cutting off supply, like a siege rather than a direct assault, patient and effective, gradually transforming the galaxy without dramatic disruption. Galaxies might form thick disks through heating of thin disks. The thick stellar disks observed in many galaxies, including the Milky Way, might form when thin disks are heated by gravitational perturbations. This theory proposes that interactions with satellite galaxies, giant molecular clouds, or spiral arms can scatter stars out of the thin disk, increasing their vertical motions and creating a thicker distribution. Over time, repeated perturbations heat the disk, gradually building up a thick disk component. The thick disk would contain older stars as they've had more time to be heated, while the thin disk would contain younger stars that haven't yet experienced significant heating. The theory can explain the observed properties of thick disks, including their greater scale heights, older stellar populations, and different chemical compositions compared to thin disks. An alternative theory suggests thick disks form during an early phase of intense star formation, when the galaxy's disk was turbulent and unstable. But the heating theory might explain thick disks in galaxies that show no evidence for such early turbulence. Understanding thick disk formation helps reconstruct the dynamical history of galaxies, revealing how their structure has evolved over billions of years through the cumulative effects of countless small perturbations. Galaxies might merge along specific orbital configurations. The outcome of a galaxy merger might depend critically on the orbital parameters of the collision, including the impact angle, relative velocity, and spin orientations. This theory proposes that head-on collisions produce different results than glancing blows, and that the alignment of the galaxy's spins affects how efficiently the merger triggers star formation and how the remnant is structured. Simulations show that prograde mergers, where the galaxy's spins are aligned, produce different remnants than retrograde mergers with anti-aligned spins. The theory suggests that the diversity of galaxy morphologies and properties might partly reflect the diversity of merger configurations, with each type of collision producing a different type of remnant. Understanding these orbital dependencies is crucial for interpreting observations of merging systems and predicting the outcomes of future mergers. The theory emphasizes that galaxy mergers are not uniform events, but vary depending on the specific circumstances of each collision. The same two galaxies might produce different remnants if they collided from different angles or with different relative velocities, adding another dimension to the complexity of galaxy evolution. Another variable in the equation that determines a galaxy's fate. Galaxies might form shells and ripples from minor mergers. When a small galaxy merges with a larger one, it might create shell-like structures and ripples in the larger galaxy's stellar distribution. This theory proposes that these features form when the smaller galaxy is disrupted and its stars are deposited in phase space, creating patterns that appear as shells when viewed in projection. The shells and ripples are transient features, gradually fading as the stars mix into the larger galaxy's halo, but they can persist for billions of years, providing evidence of past mergers. Observations show that many elliptical galaxies have shell structures, suggesting that minor mergers are common. The theory provides a way to estimate the time since the merger based on the shell's properties, as their spacing and contrast depend on how long ago the merger occurred. Shells are like echoes of past mergers, patterns that reverberate through the galaxy long after the event that created them. They're reminders that galaxies carry their history in their structure, that the past is never completely erased but leaves traces that careful observation can reveal, ghostly patterns written in starlight, fading but not yet gone, slowly dissolving back into the smooth background. Galaxies might have their properties determined by their dark matter. Halos, the properties of a galaxy, might be largely determined by the properties of its dark matter halo, with the visible galaxy simply reflecting the halo's characteristics. This theory proposes that halo mass determines galaxy mass, halo concentration affects galaxy structure, and halo spin influences galaxy morphology. The visible galaxy is almost a passive tracer of the underlying dark matter distribution, its properties set by the halo in which it formed. This view emphasizes the importance of dark matter in galaxy formation, and suggests that understanding galaxies requires understanding their dark matter halos. The theory can explain many observed correlations between galaxy properties, as these correlations might ultimately derive from correlations between halo properties. However, the relationship between galaxies and their halos is not perfectly deterministic, as galaxies of similar halo mass can have different properties, indicating that baryonic physics also plays a role. Nevertheless, the halo provides the foundation, the stage on which the galaxy's evolution plays out. Understanding this relationship between visible galaxies and invisible halos is one of the central challenges in modern astrophysics, connecting the visible cosmos we observe to the dark scaffolding that underlies it. There's no test at the end, no need to prove you were listening. Your mind can wander where it wants, to memories, to dreams, to nothing at all. Galaxies might form. Multiple generations of star clusters. Globular clusters, dense spherical collections of stars orbiting galaxies, might form in multiple episodes rather than all at once. This theory proposes that galaxies can form new globular clusters during major mergers or intense starburst events, creating younger populations that coexist with ancient clusters formed during the galaxy's initial assembly. These multiple generations would have different ages, chemical compositions and spatial distributions reflecting the different conditions during their formation. Observations of some galaxies show evidence for bimodal or multimodal globular cluster populations supporting this theory. The younger clusters might form from gas compressed during galaxy interactions, while older clusters represent the galaxy's initial star formation. The theory suggests that globular cluster systems are not static, but can grow and evolve throughout a galaxy's lifetime. Each generation of clusters is a fossil record of a particular epoch in the galaxy's history, a snapshot of conditions at that time, preserved in the properties of stars that have remained bound together for billions of years. By studying globular cluster populations, astronomers can reconstruct the merger histories and star formation histories of their host galaxies, reading the past in these ancient stellar cities. Galaxies might experience fountain. Flows of gas in galaxies might circulate in fountain-like flows, where gas is expelled from the disk by supernovae and stellar winds, rises into the halo, cools, and falls back to the disk. This theory of galactic fountains proposes that this cycling of gas is a fundamental process in galaxy evolution, regulating star formation and enriching the halo with metals. The fountain flows create a connection between the disk and halo, preventing them from evolving independently. Gas expelled from the disk carries metals produced by stars, enriching the halo with heavy elements. When this gas falls back, it brings these metals back to the disk, affecting the composition of future generations of stars. The theory suggests that galaxies breathe, inhaling and exhaling gas in a continuous cycle that extends throughout their lives. The fountain flows might help explain the metallicity distribution in galactic halos and the presence of intermediate velocity clouds observed around the Milky Way. They represent another form of feedback, where star formation affects its own future by altering the properties of available gas, creating a self-regulating system that maintains star formation over billions of years without exhausting the gas supply too quickly. Galaxies might form stars in molecular clouds. Star formation in galaxies might occur exclusively in molecular clouds, dense regions where hydrogen exists in molecular rather than atomic form. This theory proposes that the transition from atomic to molecular hydrogen is a crucial step in the star formation process, and that understanding this transition is key to understanding why galaxies form stars at the rates they do. Molecular clouds provide the cold, dense conditions necessary for gravitational collapse to overcome thermal pressure and form stars. The theory suggests that factors affecting molecular cloud formation, such as the strength of ultraviolet radiation fields and the availability of dust to shield molecules from dissociating photons, indirectly control star formation rates. Galaxies with more molecular gas form more stars, while galaxies where gas remains atomic form fewer stars, even if they have similar total gas masses. The theory emphasizes the importance of gas phase in determining star formation, adding another layer to our understanding of the complex process by which galaxies convert gas into stars. Molecular clouds are the wombs of stars, the specific environments where conditions are right for creation, their formation and destruction pacing the birth of new stars across the galaxy. Galaxies might be shaped by feedback from stellar winds. Before supernovae explode, massive stars produce powerful stellar winds that can affect their surroundings. This theory proposes that these winds, collectively from millions of stars, provide significant feedback that shapes galaxy evolution. Stellar winds can heat gas, create bubbles and cavities in the interstellar medium, and drive outflows from the galaxy. Unlike supernovae, which provide impulsive bursts of energy, stellar winds operate continuously throughout a massive star's lifetime, providing sustained pressure on surrounding gas. The theory suggests that stellar winds might be particularly important in low-mass galaxies, where the gravitational potential is shallow and gas can be more easily expelled. Stellar wind feedback might help explain why low-mass galaxies are less efficient at forming stars than their gas content would suggest. The winds prevent some gas from collapsing to form stars, reducing the overall star formation efficiency. Including stellar winds in simulations of galaxy formation changes the predicted properties of galaxies, bringing them into better agreement with observations. The theory emphasizes that feedback comes in multiple forms, not just from supernovae, but from the steady pressure of stellar winds, a gentler but persistent force shaping the galaxy. Galaxies might have different metallicity gradients. The abundance of heavy elements in galaxies might vary with radius, creating metallicity gradients that reveal information about galaxy evolution. This theory proposes that metallicity gradients form because star formation occurs at different rates in different parts of the galaxy, and because metals produced in the inner galaxy don't mix efficiently to the outer regions. The inner galaxy, where star formation is more intense, becomes more metal-rich, while the outer galaxy remains more pristine. The steepness of the gradient depends on the galaxy's star formation history, gas inflow and outflow patterns, and the efficiency of mixing. Observations show that most spiral galaxies have negative metallicity gradients, with metal abundance decreasing outward, consistent with inside-out growth. However, some galaxies show flatter gradients or even positive gradients, suggesting different evolutionary histories. The theory of metallicity gradients connects chemical evolution to structural evolution, linking the distribution of elements to the processes that built the galaxy. Measuring gradients in distant galaxies allows astronomers to study how they've evolved over time, comparing gradients in the early universe to those in the present day, tracing the chemical enrichment history of galaxies across cosmic time. Galaxies might form through smooth accretion of cold gas. Rather than growing primarily through mergers, some galaxies might assemble mass through smooth accretion of cold gas from the intergalactic medium. This theory proposes that gas flows along cosmic web filaments directly into galaxies, providing a steady supply of fuel for star formation without the disruption of mergers. The accreted gas settles into the galactic disk, extending it and maintaining star formation over billions of years. This process might be particularly important for galaxies that haven't experienced major mergers, allowing them to grow gradually through accretion alone. The theory suggests that there are two main modes of galaxy growth: smooth accretion and mergers, with different galaxies dominated by different modes depending on their mass and environment. Lower mass galaxies in less dense environments might grow primarily through smooth accretion, while massive galaxies in dense environments grow more through mergers. The balance between these modes determines the galaxy's morphology, structure, and star formation history. Understanding the relative importance of smooth accretion versus mergers is crucial for building accurate models of galaxy formation. The theory emphasizes that galaxy growth is not always violent but can be gentle and gradual, a steady accumulation rather than sudden acquisition. Galaxies might experience AGN feedback in radio mode. Besides the quasar mode of feedback, active galactic nuclei might also provide feedback in a radio mode, where jets of relativistic particles heat gas in the galactic halo. This theory proposes that radio mode feedback operates at lower accretion rates than quasar mode, and might be important for maintaining quiescence in massive galaxies. The radio jets inflate bubbles in the hot gas surrounding the galaxy, preventing it from cooling and falling back into the galaxy to form stars. This process, called radio mode feedback or maintenance mode feedback, might explain why the most massive galaxies remain red and dead rather than gradually accumulating gas and resuming star formation. The feedback prevents cooling flows, maintaining the galaxy in a quiescent state over billions of years. Observations of galaxy clusters show evidence for this process, with X-ray observations revealing cavities in the hot gas coinciding with radio lobes from the central galaxy's jets. The theory suggests that supermassive black holes continue to influence their host galaxies even after the quasar phase ends, their jets providing a gentle but persistent heating that prevents renewed star formation, maintaining the galaxy's quiescent state, a thermostat regulating the galaxy's temperature, and preventing it from cooling enough to form new stars. Galaxies might form through hierarchical merging of protogalactic fragments. In the early universe, galaxies might have formed from the merging of numerous small protogalactic fragments, rather than from the collapse of a single large cloud. This theory of hierarchical formation proposes that the first structures to form were small, roughly the mass of globular clusters or dwarf galaxies, and that these fragments then merged to form larger galaxies. The process would have been chaotic, with fragments merging in random orientations, potentially explaining the diversity of galaxy morphologies and structures. Each fragment would have brought its own stars, gas, and dark matter, contributing to the growing galaxy. The theory predicts that the earliest phases of galaxy formation were dominated by mergers, with smooth accretion becoming more important later. Observations of the most distant galaxies, seen as they were in the early universe, show irregular, clumpy structures that might represent this early phase of assembly. The theory connects galaxy formation to the broader picture of structure formation in the universe, where small structures form first and larger structures assemble from them, a bottom-up process that builds galaxies from smaller building blocks, each merger adding mass and complexity, gradually creating the large galaxies we observe today. Galaxies might contain intermediate-age stellar populations. Between the ancient stars formed during the galaxy's initial assembly and the young stars forming today, galaxies might contain significant populations of intermediate-age stars. This theory proposes that these populations, formed several billion years ago, provide crucial information about the galaxy's middle history, a period that's often less well studied than either the earliest or most recent epochs. Intermediate-age stars might have formed during a particular episode of star formation, triggered by a merger or during a period of enhanced accretion. Their properties, including their chemical compositions and spatial distributions, can reveal what conditions were like in the galaxy at that time. The theory emphasizes that galaxy evolution is not just about the extremes of the oldest and youngest stars, but about the continuous history spanning billions of years. Each epoch of star formation adds a layer to the galaxy's structure, and studying all these layers is necessary for understanding the complete history. Intermediate-age populations are like middle chapters in the galaxy's story, connecting the beginning to the present, filling in the narrative between formation and today, their presence reminding us that galaxies have lived long, complex lives with many chapters, each worth reading, each contributing to the full story. Galaxies might have their star formation regulated by dust. The dust in galaxies, composed of tiny solid grains formed in stellar atmospheres and supernovae, might play a crucial role in regulating star formation. This theory proposes that dust affects star formation in multiple ways, by shielding molecular clouds from dissociating radiation, by providing surfaces where molecules can form, and by cooling gas through infrared emission. Without dust, molecular clouds might not form efficiently, and star formation would be suppressed. The dust abundance in a galaxy depends on its star formation history, as dust is produced by stars and destroyed by supernovae and other processes. The theory suggests a feedback loop where star formation produces dust, which enables more star formation, but also where dust destruction limits star formation. Understanding this cycle is crucial for understanding why galaxies form stars at the rates they do. Dust also affects how we observe galaxies, absorbing and scattering light, making galaxies appear redder and dimmer than they would without dust. Correcting for dust extinction is necessary for accurately measuring galaxy properties. The theory emphasizes that dust is not just a contaminant that complicates observations, but an active participant in galaxy evolution, a component whose presence or absence significantly affects how galaxies evolve. Galaxies might form in resonance with dark matter substructure. The formation and evolution of galaxies might be influenced by dark matter substructure, smaller dark matter clumps within the larger halo. This theory proposes that these subhalos, remnants of smaller dark matter halos that merged with the main halo can affect the galaxy's disk through gravitational interactions. Subhalos passing through the disk can heat it, thicken it, or trigger spiral arms and other instabilities. The theory suggests that the abundance and properties of subhalos might influence how galaxies evolve, with galaxies in halos with more substructure experiencing more dynamical heating and disruption. Simulations predict that dark matter halos should contain numerous subhalos, though most would be too small and dark to observe directly. Their presence would be inferred from their gravitational effects on the visible galaxy. The theory connects galaxy evolution to the properties of dark matter on small scales, suggesting that understanding galaxies requires understanding the full dark matter distribution, not just the smooth halo but also its substructure. These dark matter clumps would be invisible architects shaping the galaxy through gravity alone, their influence subtle but cumulative, gradually affecting the galaxy's structure over billions of years. If you've drifted in and out, that's perfect. These theories are companions, keeping you company as you drift, asking nothing, demanding nothing, just offering gentle wonder. Galaxies might experience pre-processing in groups before joining clusters. Before galaxies fall into massive clusters, they might be members of smaller groups, and their time in these groups might significantly affect their properties. This theory of pre-processing proposes that group environments can quench star formation, remove gas, and alter morphologies before galaxies enter clusters. By the time they arrive in the cluster, some galaxies might already be red and gas-poor, their transformation having occurred in the group rather than in the cluster itself. This complicates the interpretation of environmental effects, as the cluster environment might not be directly responsible for all the transformations observed in cluster galaxies. The theory emphasizes the importance of considering a galaxy's full environmental history rather than just its current location. Groups are intermediate density environments, more crowded than the field but less extreme than clusters, and they might represent an important stage in environmental processing. Understanding pre-processing requires studying galaxies in groups and tracking how their properties change as they fall into clusters. The theory suggests that galaxy evolution is a cumulative process, with each environment leaving its mark, the final state reflecting the sum of all influences experienced throughout the galaxy's journey through the cosmic web. Galaxies might form stars in nuclear rings. Some galaxies contain rings of intense star formation surrounding their nuclei, and these nuclear rings might represent a distinct mode of star formation. This theory proposes that nuclear rings form at resonances in the galactic disk, locations where the orbital frequencies of stars and gas match the pattern speed of a bar or spiral structure. Gas accumulates at these resonances, reaching high densities that trigger star formation. The rings can be remarkably circular and narrow, concentrating star formation in a well-defined region. The theory suggests that bars are particularly effective at driving gas into nuclear rings, funneling material from the outer disk toward the center where it accumulates at the inner Lindblad resonance. Nuclear rings might be transient features, forming when a bar is strong and dissipating when the bar weakens, or when the accumulated gas is consumed by star formation. Observations show that nuclear rings are common in barred galaxies, supporting the connection between bars and rings. The theory highlights the importance of non-axis emetric structures, like bars in redistributing gas within galaxies and concentrating star formation in specific locations. Nuclear rings are like cosmic racetracks, where gas circles the galactic center at high speed, compressed and heated, forming stars in a narrow lane. Galaxies might have different timescales for star formation. The timescale over which a galaxy converts its gas into stars might vary significantly between galaxies and might determine many of their observable properties. This theory proposes that some galaxies form stars quickly, exhausting their gas in 1 billion years or less, while others form stars slowly, maintaining star formation for 10 billion years or more. The star formation timescale depends on factors like gas density, turbulence, feedback efficiency, and the rate of gas accretion. Galaxies with short timescales become red and quiescent early, while galaxies with long timescales remain blue and star-forming to the present day. The theory suggests that understanding what determines the star formation timescale is crucial for understanding galaxy diversity. Observations show a wide range of specific star formation rates, the rate per unit mass among galaxies, indicating different timescales. The theory connects the star formation timescale to the efficiency of feedback processes, proposing that strong feedback lengthens the timescale by removing or heating gas, while weak feedback allows rapid star formation. Understanding these timescales helps explain why galaxies of similar mass can look so different, their appearances reflecting different paces of evolution, some racing through their lives, others taking their time. Galaxies might form in biased locations in the cosmic web. Galaxies might not form randomly throughout the cosmic web, but preferentially in certain locations, a process called biased galaxy formation. This theory proposes that galaxies form more efficiently in regions of higher dark matter density, such as the nodes and filaments of the cosmic web, while voids remain relatively empty. The bias depends on galaxy mass, with massive galaxies more strongly biased toward dense regions than low-mass galaxies. This creates a spatial distribution where galaxy clustering strength depends on galaxy properties, with red, massive galaxies more clustered than blue, low-mass galaxies. The theory explains the observed large-scale structure of the galaxy distribution and provides a way to connect galaxy properties to their environments. Understanding galaxy bias is crucial for using galaxy surveys to map the underlying dark matter distribution and for interpreting measurements of cosmic structure. The theory suggests that a galaxy's location in the cosmic web is not random but reflects the conditions of its formation, with different types of galaxies preferring different environments. This spatial segregation of galaxy types reveals the connection between galaxy properties and the large-scale structure of the universe, showing that where a galaxy lives is intimately connected to what kind of galaxy it is. Galaxies might experience multiple mergers. Throughout their lives, rather than experiencing a single major merger, galaxies might undergo multiple mergers of varying mass ratios throughout their lifetimes. This theory proposes that galaxy growth is a cumulative process, with each merger contributing mass and altering structure, the final galaxy reflecting the sum of all these events. Major mergers, where the mass ratio is close to 1:1, have dramatic effects, potentially transforming spirals into ellipticals. Minor mergers, where one galaxy is much smaller than the other, have more subtle effects but might be more common. The theory suggests that most galaxies have experienced at least one major merger and numerous minor mergers by the present day. Each merger leaves signatures in the galaxy's structure, stellar populations and kinematics, creating a complex fossil record. Disentangling this record requires sophisticated observations and modelling, comparing observed properties to predictions from simulations of different merger histories. The theory emphasizes that galaxy evolution is not a simple linear process, but a complex history of multiple events, each contributing to the final product. Understanding individual galaxies requires reconstructing their merger trees, the branching histories showing all the galaxies that merged to create the present system, a genealogy written in stars and structure. Galaxies might form through disk. Instabilities in the early universe. In the early universe, when gas fractions were higher and disks were more unstable, galaxies might have formed stars through disk-wide instabilities rather than through localized molecular clouds. This theory proposes that these instabilities created giant clumps of gas and stars, massive enough to be visible as distinct structures within the galaxy. The clumps would migrate inward due to dynamical friction, eventually merging with the central bulge or dispersing their mass throughout the disk. This process, called violent disk instability, might have been the dominant mode of star formation in the early universe, explaining the clumpy appearance of high redshift galaxies observed with powerful telescopes. As the universe aged and gas fractions decreased, this mode became less important, and star formation transitioned to the more quiescent, molecular cloud-based mode observed in present-day galaxies. The theory suggests that galaxy evolution includes a transition from early, violent star formation to later, calmer star formation, with the transition occurring at different times for different galaxies depending on their gas accretion histories. Understanding this transition is crucial for connecting the high redshift galaxy population to present-day galaxies, tracing how galaxies evolve from their chaotic youth to their more orderly present state. Galaxies might contain dark matter, annihilation signals. If dark matter consists of particles that can annihilate with each other, galaxies might emit gamma rays or other signals from these annihilations. This theory proposes that the centers of galaxies, where dark matter density is highest, might be sources of detectable annihilation radiation. The signal strength would depend on the dark matter particle's properties, including its mass and annihilation cross-section, as well as the dark matter density profile in the galaxy. Detecting such signals would provide direct evidence for dark matter's particle nature and constrain its properties. Searches for dark matter annihilation signals focus on galaxies with high dark matter densities and low astrophysical backgrounds such as dwarf spheroidal galaxies. So far, no definitive detection has been made, but the searches continue, refining techniques and expanding to more targets. The theory connects particle physics to astrophysics, suggesting that galaxies might serve as laboratories for detecting dark matter particles. If successful, these searches would revolutionize our understanding of dark matter, transforming it from a gravitational phenomenon to a particle that can be studied through its interactions. A bridge between the cosmos and the quantum realm connecting the largest and smallest scales of physics. Galaxies might form, stars in superbubbles. Expanding shells of hot gas created by multiple supernovae called superbubbles might trigger star formation in their compressed walls. This theory proposes that superbubbles are not just destructive but also creative, their expansion compressing surrounding gas and triggering new generations of stars. The process creates a feedback loop where star formation leads to supernovae, which create superbubbles, which trigger more star formation. This sequential star formation might propagate through the galaxy, creating chains of star-forming regions linked by their common origin in superbubbles. The theory suggests that superbubbles play a dual role in galaxy evolution, both providing negative feedback by heating and dispersing gas, and positive feedback by triggering star formation. The balance between these effects might vary depending on the superbubble's size, expansion velocity, and the properties of surrounding gas. Observations show that some star-forming regions are indeed located on the edges of superbubbles, supporting the theory. Understanding superbubbles' role in star formation requires detailed observations of their structure and kinematics, as well as simulations that can follow the complex interplay between expansion, compression, and star formation, tracking how energy from dying stars influences the birth of new ones. Galaxies might undergo morphological transformations without mergers. A galaxy's morphology might change significantly over time, even without major mergers, through processes like bar formation, disk instabilities, and secular evolution. This theory proposes that galaxies are not static objects, but continuously evolving systems whose structures change in response to internal processes. A spiral galaxy might develop a bar, which then funnels gas to the center, building a bulge and potentially transforming the galaxy from a pure disk to a disk plus bulge system. The bar itself might later dissolve, leaving behind a galaxy with a different structure than when it started. The theory emphasizes that morphology is not a fixed property, but evolves throughout a galaxy's life. Understanding morphological transformations requires long-term observations or comparisons between galaxies at different distances and thus different cosmic times. The theory suggests that the Hubble sequence of galaxy types might not represent an evolutionary sequence, but rather a snapshot of galaxies caught at different stages of internal evolution and at different points in their merger histories. Morphology reflects both a galaxy's history and its present state, a combination of what it has experienced and what processes are currently operating within it, a portrait that changes slowly but continuously over billions of years. We're near the end now. Let the final theories wash over you like gentle waves, carrying you deeper into rest, into calm, into the soft embrace of sleep. Galaxies might form through cosmic recycling. Matter in galaxies might be recycled multiple times, passing through stars, being expelled in winds, falling back, and forming new stars in an endless cycle. This theory proposes that galactic evolution is not a one-way process of converting gas into stars, but a cyclical process where matter moves between different phases and locations. A hydrogen atom might be part of a star, be expelled in a supernova, spend millions of years in the hot halo, cool and fall back to the disk, become part of a molecular cloud, and form a new star. The theory suggests that the matter in galaxies has complex histories, with individual atoms participating in multiple generations of stars. This recycling enriches the gas with metals, gradually increasing the metallicity over time. It also extends the star formation timescale, allowing galaxies to form stars over billions of years rather than exhausting their gas quickly. Understanding cosmic recycling requires tracing matter through different phases and locations, following its journey through the galaxy. The theory emphasizes that galaxies are not closed systems, but dynamic environments where matter circulates, transforms, and recirculates, never static, always flowing, a cosmic water cycle written in gas and stars and energy. Galaxies might be shaped by cosmic rays from supernovae, cosmic rays, high-energy particles produced primarily by supernovae, might provide significant pressure support in galactic disks and drive galactic winds. This theory proposes that cosmic ray pressure is comparable to thermal and magnetic pressure in some regions of galaxies, making cosmic rays an important component of the interstellar medium's energy budget. Cosmic rays can diffuse through the galaxy, carrying energy far from their production sites and affecting gas dynamics in distant regions. They might help launch galactic winds by providing additional pressure to push gas out of the disk. The theory is challenging to test because cosmic rays are difficult to observe directly in other galaxies, but their effects on gas dynamics might be inferred from observations of gas kinematics and from simulations that include cosmic ray physics. Including cosmic rays in galaxy simulations changes the predicted properties of galaxies, suggesting they play a non-negligible role in galaxy evolution. The theory adds another layer to the complex physics of galactic feedback, another way that star formation affects its own environment and future, another invisible force shaping the visible cosmos. Galaxies might form in resonance with cosmic expansion. The formation of galaxies might be intimately connected to the expansion of the universe, with structure formation occurring when the expansion rate and gravitational collapse timescales are comparable. This theory proposes that galaxies formed during a specific epoch in cosmic history when conditions were right for gravitational collapse to overcome expansion. Before this epoch, the universe expanded too rapidly for structures to form. After this epoch, dark energy began to dominate, accelerating expansion and making it harder for new structures to form. The theory suggests that the present-day galaxy population formed during a relatively narrow window in cosmic history, roughly between 1 and 10 billion years after the Big Bang. Understanding this timing is crucial for understanding why galaxies have the properties they do, as their formation epoch determined the conditions they experienced during assembly. The theory connects galaxy formation to cosmology, showing that galaxies are not just objects within the universe, but products of the universe's evolution, their existence and properties determined by cosmic history, children of the expanding universe. formed when expansion and gravity balanced, allowing structure to emerge from the smooth early cosmos. Galaxies might contain multiple rotating components. A single galaxy might contain several distinct components, each rotating independently or at different speeds. This theory proposes that galaxies are composite systems, with thin disks, thick disks, bulges and halos, each having different kinematic properties. The components might have formed at different times or from different sources, creating a complex structure where multiple populations coexist. The thin disk rotates rapidly. The thick disk rotates more slowly, and the halo might have little net rotation. Understanding how these components formed and how they interact requires detailed observations of stellar kinematics, measuring velocities for large numbers of stars and decomposing the galaxy into its constituent parts. The theory suggests that galaxies are not simple objects, but layered structures, each layer telling part of the story. The components might exchange mass and energy through dynamical processes, gradually evolving toward equilibrium but never quite reaching it. The theory emphasizes that understanding a galaxy requires understanding all its components, not just the most visible or most massive. Each component contributes to the galaxy's total structure and evolution. Each plays a role in the full story. Each deserves attention and study. Galaxies might experience tidal shocking from dark matter. Subhalos. Dark matter subhalos passing through a galaxy's disk might deliver impulsive gravitational shocks that heat the disk and alter its structure. This theory proposes that these tidal shocks, though brief, can have cumulative effects over billions of years, gradually thickening the disk and increasing stellar velocity dispersions. The frequency and strength of shocks depend on the abundance and masses of subhalos, connecting disk structure to the properties of dark matter on small scales. The theory provides a mechanism for disk heating that doesn't require visible satellites, as most subhalos would be too dark to observe directly. Their presence would be inferred from their effects on the disk rather than from direct detection. Simulation suggests that tidal shocking might be important for understanding disk evolution, particularly for explaining why some disks are thicker or hotter than expected based on their visible satellite populations. The theory highlights the hidden influence of dark matter substructure, suggesting that the visible galaxy is affected by dark matter in ways beyond the smooth halo's gravity. These invisible impacts gradually reshape the galaxy, each shock a small perturbation, but the cumulative effect significant, a slow drumbeat of dark matter's influence. Galaxies might form stars. In response to external pressure, gas in galaxies might be compressed by external pressure from the surrounding medium, triggering star formation. This theory proposes that ram pressure or other environmental forces don't just strip gas but can also compress it, potentially enhancing star formation before eventually removing it. Galaxies falling into clusters might experience an initial burst of star formation, as ram pressure compresses their disks, followed by quenching as the gas is stripped away. This creates a two-phase process where environmental effects first enhance, then suppress star formation. The theory can explain observations of galaxies in cluster outskirts that show elevated star formation rates, suggesting they're in the compression phase. Understanding the balance between compression and stripping requires detailed observations of gas kinematics and star formation. Rates in galaxies at different distances from cluster centers. The theory emphasizes that environmental effects are complex, not simply destructive but potentially creative in their early stages. The environment shapes galaxies through multiple mechanisms operating simultaneously, compression and stripping working together, their relative importance varying with location and time, creating a complex pattern of environmental influence that changes as galaxies fall deeper into clusters. Galaxies might have their evolution determined by initial conditions. The properties of galaxies might be largely determined by their initial conditions at formation, with subsequent evolution simply revealing or amplifying these initial differences. This theory proposes that factors like the initial mass, angular momentum, and density of the protogalactic cloud set the galaxy on a particular evolutionary track. High initial angular momentum might lead to extended disk formation, while low angular momentum might produce compact systems. High initial density might lead to rapid star formation and early quenching, while low density might allow prolonged star formation. The theory suggests that much of the diversity in galaxy properties reflects diversity in initial conditions, rather than different evolutionary paths from similar starting points. Understanding initial conditions requires studying the earliest phases of galaxy formation, observing the most distant galaxies, and running simulations that trace galaxies from their earliest moments. The theory emphasizes that to understand why galaxies are the way they are, we must understand where they came from, that the present is connected to the beginning, that the seeds of a galaxy's future are planted at its birth, determining possibilities and constraints that echo through billions of years galaxies might experience. Quenching through halo. Mass. Quenching above a certain dark matter halo mass, galaxies might stop forming stars regardless of their environment. This theory of halo mass quenching proposes that massive halos prevent gas from cooling and accreting onto the central galaxy, shutting down star formation. The mechanism might involve shock heating of infalling gas, or prevention of cold mode accretion by the halo's deep potential well. Galaxies in massive halos would become red and quiescent, even if they're isolated, not requiring environmental effects like ram pressure stripping. The theory can explain why the most massive galaxies are almost always red and dead, regardless of where they live. It suggests a mass threshold above which galaxies cannot maintain star formation, a fundamental limit to galaxy growth. Understanding halo mass quenching requires connecting galaxy properties to halo properties, using techniques like abundance matching or weak gravitational lensing to infer halo masses. The theory provides a path to quiescence that doesn't require environmental effects, suggesting that internal processes alone can shut down star formation in massive systems. The galaxy's own mass becomes its limiting factor, its gravity so strong that it prevents the gentle accretion needed to sustain star formation, choking off its own future growth. Galaxies might form through competitive accretion. In dense environments, galaxies might compete for gas, with the most massive galaxies accreting gas at the expense of their smaller neighbours. This theory of competitive accretion proposes that gas flows preferentially toward the deepest potential wells, feeding massive galaxies while starving smaller ones. This creates a rich-get-richer scenario where massive galaxies grow faster, increasing the mass gap between large and small galaxies over time. The theory might explain the formation of the most massive galaxies in the universe, central galaxies in clusters that seem to have accreted gas from a large volume. It suggests that galaxy growth is not just about internal processes, but about competition with neighbours, about winning or losing in the struggle for resources. Understanding competitive accretion requires simulating the gas dynamics in galaxy groups and clusters, tracking how gas flows between galaxies and how accretion rates depend on galaxy mass and position. The theory emphasizes that galaxies don't evolve in isolation, but in communities where interactions and competition shape outcomes. The strongest survive and grow, the weaker starved and fade, a cosmic ecology where resources are limited and success breeds success, shaping the galaxy population through competition as much as through internal evolution. Galaxies might be windows into dark energy's nature. The evolution of galaxies over cosmic time might provide clues about dark energy's properties and how it has affected structure formation. This theory proposes that dark energy's influence on cosmic expansion affects when and how galaxies form, potentially leaving signatures in the galaxy population that can be used to constrain dark energy's equation of state. By studying how galaxy properties change with cosmic time, astronomers might learn about dark energy's history and nature. The theory connects the small-scale physics of galaxy formation to the large-scale physics of cosmic expansion, suggesting that galaxies carry information about fundamental cosmology. Understanding this connection requires comparing observations of galaxies at different distances to predictions from cosmological models with different dark energy properties. The theory suggests that galaxies are not just interesting objects in their own right, but tools for understanding the universe's fate. Their evolution over billions of years records the influence of dark energy, their properties shaped by the accelerating expansion, their futures determined by whether dark energy remains constant or changes with time, each galaxy a small window into cosmic destiny. Galaxies might end in isolation and darkness. In the far future, as dark energy continues accelerating cosmic expansion, galaxies might become isolated islands in an expanding void. This theory describes the ultimate fate of galaxies in an accelerating universe, where all galaxies not gravitationally bound to each other eventually lose contact, receding beyond each other's cosmic horizons. Within billions of years, observers in distant galaxies will see only their local group, the rest of the universe having disappeared beyond reach. The sky will darken as distant galaxies fade from view, their light unable to catch up with expanding space. Eventually, even nearby galaxies will merge, creating isolated elliptical galaxies surrounded by darkness. Star formation will cease as gas is exhausted, and the galaxies will fade, their stars dying one by one, leaving only cold remnants. The theory paints a lonely future for galaxies, each one eventually alone in an expanding universe, all connections severed, all companions gone, surrounded by growing darkness. It's a distant fate, trillions of years away, but written in the current acceleration, an ending of isolation and cold, where galaxies drift alone through infinite space, their light fading, their warmth dying, slowly dissolving into the dark, patient and eternal, waiting at the end of time. And so our quiet journey through galaxies comes to a gentle close. We've travelled far tonight, from spiral arms and dark matter halos to cosmic webs and distant futures, touching on questions that span billions of light years and billions of years, mysteries written in starlight and gravity. The theories behind us now, like stars fading into dawn, their details softening, their specifics blurring into a general sense of cosmic wonder. Some theories offered answers, others only deeper questions. Some felt solid, grounded in observation and simulation. Others shimmered like possibilities, suggestions of what might be rather than what is. But all of them carried a piece of humanity's endless curiosity, our refusal to accept the universe at face value, our need to wonder and question, and reach toward understanding. These theories, some ancient and some born yesterday, represent our attempts to understand how galaxies form, evolve, live and die, how they relate to each other and to the larger cosmos, how they came to be and what they will become. Theories are strange things, aren't they? They're not quite facts, not quite fantasies. They live in the space between what we know and what we imagine, between observation and speculation, between certainty and possibility. They're humanity's way of reaching toward truth with imperfect hands, building bridges across chasms of ignorance with the materials we have available, knowing the bridges might not reach all the way across, but building them anyway. Some theories will be proven right, confirmed by future observations, elevated to the status of established knowledge. Others will fade, replaced by better ideas, remembered only as stepping stones on the path to understanding. But the reaching itself, the wondering, the questioning, never stops. It continues as long as there are minds to wonder, as long as there are mysteries to contemplate, as long as galaxies shine in the darkness, inviting us to understand them. If your eyes are already heavy, that's just fine. Perfect, even. Let the last traces of spiral arms and cosmic webs fade behind your thoughts, becoming less distinct, less important, dissolving into the general darkness behind your eyelids. Let your breath carry you softly into rest, each exhale releasing a little more tension, a little more of the day's weight, each inhale drawing you deeper into calm, deeper into the approaching sleep. There's still so much more to discover about galaxies, endless questions waiting, countless mysteries yet to be explored, but for now, you've learned enough. You've wondered enough. You've travelled far through mysteries and questions, through theories and possibilities, and galaxies can wait until morning, patient and unchanging, still spinning in the darkness, still shining across the void, ready whenever you return to them, whenever curiosity calls you back to wonder about their nature and their fate. You don't need to remember any of this, not the theory names, not the mechanisms, not the details about dark matter or star formation or galaxy mergers. They were never meant to be memorized, only experienced, like watching clouds drift across the sky, appreciated in the moment but not clung to, not held tight. What matters is not what you retain, but how you felt while listening. The gentle stimulation of curiosity, the soft pleasure of learning something new, the quiet comfort of questions asked in darkness, the peaceful rhythm of voice and silence. That's enough. That's everything. The theories themselves will fade from memory, their specifics lost, but the feeling of wonder remains. The sense of having travelled somewhere, having touched something larger than yourself, having spent time with mysteries that dwarf human concerns and human worries, putting everything into perspective, making the day's troubles seem smaller, less urgent, less important. Notice how your body has